All right, so that's a contradiction. And remember what Hall's condition required. Hall's condition requires that the open neighborhood of S, the cardinality of that set has to be at least the cardinality of S. And this has to be true for all S's in where S is a subset of U. And here we have created a set S, call it U1, such that this little result here clearly doesn't hold, and we assumed that it does, so we get a contradiction. Right, so now remember Hall's theorem is considered one of the pillars of graph theory, and it's quite a nice application in the next theorem. If G is a bipartite R-regular graph, what's an R-regular graph? It's a graph where the degree of each vertex is the same. Then G has a perfect matching. Perfect matching is a matching that where every vertex is matched. Every vertex of the graph. Okay, now Hall's condition. How do we prove this result? Right, so there's G, and G is a R-regular bipartite graph. And let's assume, let's take a subset S. Let's take a subset S of U. Take any subset S of U. Now, because your graph is regular, if we look at the degree of the graph, which is R, and you multiply it with the cardinality of S, you are essentially counting all these edges, right? Okay, all the edges you are counting. So you can basically say that is equal to the number of edges right, so that's equal to the number of edges incident with vertices in S. If we look at the open neighborhood of S, what is that set? That's a set of all these vertices, vertices that are adjacent to a vertex in this set S. So that would be an example of a vertex of vertices in the open neighborhood of S. Now, note that if you count the edges if you count the edges incident with the vertices in the open neighborhood of S, you are basically going to count, you're going to count at the very least all these edges that you counted previously. Right, so you're going to count all these edges. That is if you count the edges incident with vertices in the open neighborhood of S. So these edges that I crossed out, those will be the edges that you count when you count the number of edges incident with vertices in S, which again will be the same number of edges here. Okay, so at the very so the number of edges incident with the open neighborhood of S vertices, that will be at least that number of edges there. Okay, so basically we have that this quantity is pretty much at most this quantity here. That quantity there, and we have that relationship there, because remember now as well, counting all the edges incident with vertices there is, as I said, it's also going to count that number of edges there, and we can also possibly count more than only that number of edges. So this relationship that I've expressed here holds, and this basically implies that the cardinality of S is at most the open neighborhood of S, and this is true for all S's. So basically This is going to imply that Hall's condition holds for this bipartite graph. Okay, and that is what they are writing there. So Hall's condition holds for bipartite graph. And by the previous theorem, what do we know about Hall's condition? Right, this means that the set U can be matched to a subset of W if and only if Hall's condition holds. Okay, so this means that I can, by that previous theorem, I can go and match the set U to a subset of W. Okay, and because this is a regular bipartite graph, both partite sets have the same number of vertices. So it means that I can go and match every vertex in U to a vertex in W. So therefore, this graph is going to have a perfect matching. Right, and that is what the rest of that result is all about. Okay, so what they're saying there is what I just basically illustrated. Okay, so Hall's theorem, it turns out, has an equivalent statement in set theory, which is quite interesting. So the definition is, let S1 up until Sn be a collection of finite non-empty sets. Then we say that the set S1 up until Sn of distinct elements is called a system of distinct representatives, or abbreviated SDR, of the set S1 up until Sn, if Si within the ith S, or if Si is in the ith S, for indices I running from 1 up until n. Right, so that will be a representative if each I in the set will be within the ith S in that collection of sets there. Now, right, this example here, if you take S1 to be V1 of V2, S2 to be V2, V3, V3, V4, V4, V1, and V1, VR respectively, then this collection has no SDR. And the reason for that is, well, there are 5 sets, but there are only 4 elements in total, so you cannot get a representative for each set, because those elements have to be distinct for it to be a system of distinct representatives. Okay, so that makes perfect sense. And that brings us to the following theorem. We say a collection of finite sets, S1 up until Sn, has an SDR if and only if for all natural numbers k between 0 and n, the union of any k sets has at least k elements. So there is basically Hall's condition. You can view this as you can view this through the lenses of Hall's condition. So what we're going to do is, to prove it, we're going to construct a bipartite graph, and then we're going to show that this bipartite graph, for it to have, for the system to have a, well, the system having a an SDR is equivalent to making sure this bipartite graph has Hall's condition satisfied. Okay, now to prove the first half is easy. Okay, so let's assume that S1 up until Sn is that collection of sets. Let's assume it has an SDR, so I can go and find a representative for S1, S2 up until Sn distinct, right? And this will imply that, again, because each one of those sets has a representative, it means that if I take any k sets from S1 up until Sn, they will have well, they will have k unique or k distinct representatives, meaning that if I take their union, obviously it's then going to have at least k elements. So that part there is easy to see that. Right, so the next part, let's assume the union of any k sets have at least k elements. And now we need to show that that collection of finite sets, which is that collection there, has a system of distinct representatives. Okay, so we construct a bipartite graph with partite sets U and V respectively. So you make U the set with vertices where your vertices are the sets S1 up until Sn, and then you take W and you form W to be a set of vertices where the vertices represent the elements, all the elements within these sets here. Okay, so there's an illustration. So you've got your partite sets U and W, and basically what you do is specifically for S1, you look at all the elements in S1, and in this example here we've got 4 elements in S1, and then we join S1 to each one of these vertices here. Okay, that is how your edge set of your graph is defined. Then also for S2, you take S2, you look at all the elements in S2, you place them in W, and you join the vertex X2 with all the vertices that represent the elements of S2. And you do that for all the sets for all the vertices in U. Now, if one looks quickly, if you look by inspection, basically, if we need to just quickly try and show that Hall's condition is satisfied. Because if Hall's condition is satisfied, it means that we can then basically match the whole set U. We can match it to a subset of W, for argument's sake. Say the matching looks like that. So we can go and match, pair off the whole of U to a subset of W. And this is going to imply that we are going to have a representative we're going to have a system of distinct representatives, because we just take each matching partner of each vertex in U, and we let that be our set or our system of distinct representatives. Okay, so we just need to check that Hall's condition is satisfied, because then we can find that matching. Now recall that the union of any k the union of any k, or the union of a collection of k sets has at least k elements. So just look at this specific little example here where k, for example, k is equal to 3. If you take your set S, for argument's sake, to be S1, S2, and S3, then what is the cardinality of the open neighborhood of S? Now this argument will work in general if you take more than 3 elements. Now just take note of the following. Remember that, right, so I mean, if you look at that there, we know the union of any, if we take the union of the open neighborhoods of S1, S2, and S3 respectively, then that we know that must be, by definition, in this case, must have cardinality at least k. And in this case, k is equal to 3, right? So you can clearly see that the union of the open neighborhood of S1, S2, and S3, which is pretty much basically going to be that set, the cardinality of that is going to be at least the cardinality of S. Right. Okay, by definition, by assumption. Okay, so you can do this for any subset S because you assume the union of any K sets is going to have at least K elements in it. So therefore Hall's condition is satisfied, and by Hall's condition you're going to be able to match every vertex in U to a vertex in W, and then you just pick the matching partners as your distinct representative elements. Okay, so going back, that is what they say there. So remember how we formed the two partite sets, and you let X be in W, and you let it be adjacent to the ith vertex Si, if and only if X is an element of Si. Then obviously it will satisfy Hall's condition for all x's in U, and the reason for that is because of this assumption here. Okay, so if you take the open neighborhood of all your vertices in X, if you take the union of that, then which is pretty much basically that set there, that's always going to have at least as much elements as this in it. Okay, that should just be cardinality there. Right, so therefore there exists such a matching by the previous theorem, and so our matching partners will form the SDR. Okay, so there are some applications here with this quick example here. So the question is, given a set of boys and a set of girls, where each girl knows some of the boys, then the question is, under what condition can each of the girls get married to a boy she knows? Okay, so that's a Hall condition type problem. So what needs to happen there is if any K girls together know at least K boys. Okay, which means basically Hall's condition is satisfied. So you form again a bipartite graph with boys and girls. Now the one partite set is composed of the girls, the other one is composed of the boys, and we join a girl vertex to a boy vertex if the girl knows the boys. And pretty much that's again a bipartite graph that you need Hall's condition to be satisfied. Right, then for a natural number K, a K factor of G is a K regular spanning subgraph of G. So a spanning subgraph is a subgraph that's got just as many vertices as the graph itself, and if it's K regular, then this is called a K factor. Now remember, a one factor of G is pretty much the same as a perfect matching of G, because then it's a one regular spanning subgraph, and that translates into a matching, which by definition is a perfect matching. So the question now is, Hall's theorem gives a necessary and sufficient condition for the existence of a one factor of a bipartite graph. So let's look at it more general. What about if your graph is non-bipartite? Okay, so let's look at the following example. This graph here we claim has no perfect matching. So there we go. Right, so why does this graph have no perfect matching? Let's say it does have a perfect matching. Well, then this must be a matching edge because of that vertex there. That has to be a matching edge. Right, okay, so basically that can't be a matching edge. Right, so basically either this is a matching edge, or that's a matching edge, or that's a matching edge. Okay, so if this is a matching edge, then obviously that can't be a matching edge. Still, that can't be a matching edge. So therefore, you have to have a situation there where one of those edges is a matching edge, or that, but two can't be a matching edge. And each time there, you get that that either this vertex or that vertex or that vertex becomes unmatched. So that is going to be a problem there. Okay. So therefore, we need to look at the case of where this is, say, for argument's sake, a matching edge. Well, again, then that can't be a matching edge, and also that can also not be a matching edge. So basically, you have to have you're going to be forced to have a situation where this graph here must have a perfect matching. But you cannot, a graph that's got odd order cannot have a perfect matching. So that component there has no perfect matching. And so that takes care of that case. Right, so what happened? So basically, the only other thing that can happen is if that is basically a matching edge, then obviously that can't be, and so again you have either that, in which case that vertex is unmatched, or you've got that, and then that vertex is unmatched, or you could have that, which in this case means this vertex is unmatched. So there's definitely no perfect matching there. Now, if you delete the vertices V1 and V2, then basically this is going to be a odd component. This is going to be an odd component. Obviously, that's going to be an odd component as well. So it sort of, in this example, definitely the odd components seem to be providing us with problems when finding a perfect matching. And so basically, if we go back to the notes, we define an odd component of a graph as a component of odd order. And we're going to see that these components play a part when it comes to finding matchings. So we denote the number of odd components by K subscript O. And now we're ready to state Tutt's one-factor theorem. Okay, so when does a graph, when does it have a one-factor? In other words, when does it have a perfect matching? Now, a graph has a perfect matching if and only if the following holds. For every subset S in the vertex set of G, the number of odd components of G without S is at most the cardinality of S. If that holds, then the graph is going to have a perfect matching. Okay, so that's a necessary and sufficient condition for a graph to have a perfect matching. So we'll first assume that G has a perfect matching, and then we will show that the number of odd components of G minus S is at most the cardinality of S. So let us assume that G has a perfect matching, M, and let S be any subset of the vertex set of G, and let G1 up until Gk be all the odd components of G minus S. Now for each component Gi, there exists an edge, a matching edge, that joins a vertex in the component, the ith component, to the ith vertex in the set S that I've removed from my graph. Now remember the VI's are distinct, and this is also going to imply that the cardinality of S is going to be at least K. All right, so there you've got a representation of your graph, and S is the set of vertices that I removed, and there's my K components, And remember, if G has a perfect matching, it means that we can pair off each vertex with another vertex. Okay, so that essentially means because G1 up until GK, they have an odd number of vertices. It means that there has to be a vertex in each component that is matched to a vertex in this cut set. Because if that weren't the case, let's say there was no edge, blue edge there, then you've got only matching edges within that graph, and that would mean that the odd component has a perfect matching, which is impossible because it's odd number of vertices. Okay, so you need to have that situation there. Okay, now that's also going to imply that the cardinality of S must be at least K. Okay, because you can basically match, count that matching there, and you're going to count at least K distinct vertices in S. So the cardinality of S is at least K. Okay, so basically this implies that S, we said, is at least K, and K is the number of odd components within the graph G minus S. Okay, so we've proved the one part of the theorem. So now we're going to assume that this part holds, and then we're going to prove the reverse, which is basically that G has a perfect matching. Okay, so let's just assume to the contrary that there exists graphs satisfying star. Star is now, what is star? Star is, it satisfies this property here, that the cardinality of S is at least the number of odd components in the graph G minus S. Okay? But they have no perfect matching. So there's definitely... So, I mean, this is all... The proof is almost... It's going to be the same technique as Kuratowski's theorem. What we're going to do is, among all the counterexamples, we're going to choose the one with smallest order n. Right, so now because this rule holds for all vertex sets within the graph G, we can choose S to be empty, and if S is empty, then the number of odd components of the graph G is 0, meaning that n is even. Okay, so we can assume that n is even, and because the theorem holds for all graphs of order 2, we have that we can assume that n is at least 4. Now, let V be a vertex such that V is not a cut vertex. And let's take S to be V. Right, then if you take the number of odd components of G minus S, right, that is going to be, that's obviously going to be 1, and 1 is going to be the cardinality of S. Right, so basically there exists a non-empty set S in the vertex set of G such that we have equality there. Okay. Now, so therefore you can find such a set S so that you have equality there. Now what we do is we choose now S to be such a set that satisfies a star, double star, and we make sure that it has maximum cardinality. You choose the largest possible set that gives you equality there. Now what we do is we claim that G minus S contains only odd components. So let's assume, for argument's sake, that GI is a component of G minus S that has even order. And let's see what happens. Can we find a contradiction? Okay, so let's say GI is an even component of the graph G minus S. Okay, now remember how we chose S. Now I'll pick a vertex in GI that is not a cut vertex of GI. Now we know that all graphs of order at least 2, they've got at least one cut vertex. So basically what we can do is we can form a new set. We can take the set S and we can take the union with X. Right. And if we look at the graph G and we take the set S union X away, okay, then the number of odd components of this graph, right? The number of odd components of this graph. First of all, we're going to generate one odd component there because GI has even order, and then we've got K. We've got K odd components when we delete this whole set from G. Okay, so that is going to be there's going to be K plus 1 components, odd components, and K plus 1 is exactly the cardinality of S union X. Okay, so now what we've done is we've constructed a larger set, and this larger set is S union X, and remember we chose S to be the largest set that has the property that S is exactly equal to the number of odd components of G minus S. But now we've created a bigger S, and the bigger S we're talking about here is S union X. Okay, so that can't happen. So therefore, we may assume that there are no even components when I remove S from G. Okay, so that is what they say there. Take a non-cut vertex. And so we may assume that all those components are odd. Right, so for indices 1 up until k, let the ith S within S be the set of vertices of S that have a neighbor in G in the ith odd component. Right, so if you look at your sketch here, basically this this whole part here is your set S, and these are all my odd components. And then I go into S and I define my first S set S1 as all the vertices in S that have a neighbor in this component here. My second set is all the vertices here that have neighbors in G2. Right, so there we've got all these vertices here that have neighbors there, and please note that S1 and S2 could have an intersection where this point here could have both neighbors in G1 and a G2. And then in general you define the kth set as all the vertices that have neighbors within the kth component. And again, SK could say, for argument's sake, have an intersection with both S1 and S2, which is that vertex there. So, I mean, those are all possibilities that could happen. We're going to apply our SDR principle, system of distinct representatives. So we claim that for all L between 0 and K, the union of any L sets SI contain at least L elements. So to find that representative, that a set of representatives. So let's suppose to the contrary that for some collection of L sets, S1, S2 up until SL, let's say the union of those sets all have strictly less than L elements in it. Okay, then what we're going to do is, if we look at the odd components of G without that collection of sets, that's going to have at least, well, that number of odd components that's going to result is going to be at least L. And why is that a problem? Let's just look at a special case. Let's say take L equals 2. Let's say if we remove S, well, let's say if we take the union of S1 and S2, and that is only one vertex, say, then what happens to the number of odd components? What happens to the number of odd components if I take the graph G, and from that I remove S1 and S2? Right, so there's the example there. If both only have one element, then if you're going to delete that vertex, you're going to have at least two components. So this is going to be at least 2. Okay, but this here is strictly less than 2. And what is going to be the problem with this? This is going to be a contradiction. And why is that going to be a contradiction? This is going to imply that this is pretty much going to be, it's going to be bigger than or equal to that, right? It's going to be strictly bigger than or equal to that. And remember, we said that we assumed in the beginning that this holds for all subsets S of G. We said that this holds definitely, okay? But here we have a contradiction because we've given an example of where it's not the case, right? So you can extend this argument in general to not include only values of L equal 2, but any value of L. Okay, so basically we have that that's at least L, but that's at most L. So that's going to contradict our assumption. So hence the union of any L sets Si contains at least L elements. So therefore you can choose as distinct representative V1 up until Vk for the sets S1 up until Sk, right? So let U1 up until Uk be their respective matching partners in Gi. Right, so therefore again we have that SDR for the vertices V1 up until Vk. Okay, so now we've used Hall's theorem, and so we have an SDR. So basically, if you look at the sets S1, S2 up until Sk, you can find these sets have representatives. Say that's your first representative, S1, that's your second representative, and that is your kth representative, Sk. And again, now we can find a matching partner for each one of these representatives. Okay, and what we're going to do is we will just label them as U1, U2 up until UK respectively. Okay, so that is what they mean there by looking at their matching partners. Now what we're going to do is we're going to let HI be the ith component Gi without the vertex Ui for all indices 1 up until K. Now we say that HI has obviously even order because each component GI is odd. And then what we claim is the number of odd components of HI minus WI is at most WI for all subsets in the vertex set of HI. So let's suppose to the contrary, that there exists in WI with the number of odd components of HI minus WI being strictly bigger than WI. Now, since HI is even order, WI and the odd number of the odd components, number of odd components of HI minus WI must have the same parity. Okay, so why must these two things have the same parity? Well, if this is odd, right, you've got an odd number of odd components. So if you count all the vertices there, an odd number of odd number times an odd number is an odd number. So an odd times an odd is an odd number. Okay, and if this is even, then if you add if that is even and you add that to an odd number, it's going to be odd, which is going to contradict the fact that this is even. If this is even, then an even times an odd is even. And if this is odd, okay, then an odd plus an even is going to be an odd, which is going to contradict that. Right, so therefore these two things must have the same parity. They either must both be even or they must both be odd. This obviously implies that this must be 2 plus the coordinality of WI. And so basically what we now do is we take a new set X and we let that set X be the cut set S, union with WI, union with UI. And what we're going to do is we're going to determine the number of odd components of G minus X. Okay, so there's my, going back to my sketch there, we're looking at the ith component there, and remember we defined HI as the ith component without UI. Okay, and now what we do is we're looking at a subset WI of HI, and we're assuming that K, number of odd components of HI minus WI is is bigger than the coordinality of WI. Okay, so let's see what happens here. So we're going to take what we're going to do is we're going to take G and we're going to take away S, and we're going to take away WI, and we're going to take away UI as well, and look at the number of odd components of this new graph. So deleting that, we get, right, so we first delete the set S. Alright, so we have our components, and then what we do is we delete W, and then we delete UI. Now the colored component, the colored sections there are my number of odd components. It's the number of odd components of hi minus wi. Right. Now we said previously that the number of odd components of hi minus wi is at least the cardinality of wi plus 2. So doing this deletion, how many odd components have I gained here? Well, first of all, I've lost one of my odd components. There used to be k odd components. I've lost one of the odd components, which is the ith odd component, but I have gained all these extra odd components, and I've gained at least wi plus 2 odd components in the process. So therefore, if we go back to the notes, compared to having just deleted s, we lost the odd component gi, but we created at least wi plus 2 new odd components. So this is at least that plus that plus 1. Now remember, we said that we chose S such that S is the largest cardinality set that has the property that that is exactly equal to that. So we can replace that with that, and therefore we can replace that whole thing with that, and that is basically equal to the cardinality of that. Okay, but one important little thing is missing here. What do we know about K0, G minus X? We assumed that this property holds. Remember, we said that for all subsets S of G, we've got that the number of odd components of G minus S, we assumed this in the beginning, is always less than or equal to the cardinality of S. This is true for all such subsets S, so it's also going to be true for X. Okay, so this little thing is basically going to imply, that K0 of G minus X is going to be at most the cardinality of X, but we proved this, so it's less than or equal to the cardinality of X. So that's going to imply that K0 is going to be of G minus X is going to be exactly equal to X. And that is a contradiction because we chose S to be the largest set that has that property, and S is bigger than and X is bigger than S. So therefore that's a contradiction. Okay, so that is a contradiction to the maximality of S. So hence this holds. That holds for all Wi in that component Hi. Since Gi is we chose it to be the smallest counterexample, each Hi has a perfect matching Mi by triple star, because you can do that for all. The inductive assumption is going to apply to that. So therefore we can take each Hi, and each Hi has a perfect matching. They're all the perfect matching. Hi without Hi is basically it is Gi without that vertex. Okay, and all those graphs have perfect matchings. Okay, so we can go and match those vertices in that way, Okay, and we can also form a perfect matching there. Okay. Okay, so again we can match, although we can form a perfect matching there, and therefore now you can form a perfect matching of the whole graph by just taking these matching partners and then throwing them all together, and that is basically what is going to happen. So you can also like throw that together with all those edges there. Your matching is then your perfect matching is going to contain all those edges there that you've matched. Okay. And then in addition to that, it is going to complete the perfect matching by including all those edges there. So your graph is going to have a perfect matching, and that concludes the proof of